All right, welcome back. I hope you're having an awesome time so far. Our next speaker is Benoit Scherer. He is the founder and CEO at Quantively. Please join me in welcoming him to our virtual stage.
Hi everyone, I'm very happy today to share how at Quantively we believe that data and AI will literally transform the way radiology manages its operations. And so as you know, AI promised to revolutionize radiology, but really it hasn't happened. First, people said that it would just replace radiologists. The consensus now, I think, is more that it will augment them rather than replace them, at least at first, and that radiologists will increasingly become information specialists, augmented with AI. But honestly, today the jury is still out. There has been a lot of hype, but people begin to realize that things are not that simple. Like generalization to image generated by different scanners is hard. Causality is hard. Lots of things need to be sorted out for AI to flourish in radiology. And don't get me wrong, we need to continue to work on this and to solve these problems. But at the same time, I would say it is not clear that AI has been applied to the right problems. And that is a recent tweet from Christopher Hess. He is the chair of the Department of Radiology and Biomed Imaging at UCSF. And he says, why AI has not flourished in radiology. Turn the focus to upstream, high value, and low regret imaging applications to get traction. And from there, you can expand. And that's really something that resonates with our thinking. And one thing that is just completely crazy in radiology today is that MRI scanners, which each costs $1 to $4 million, actually take images, which is really what they are supposed to do, less than 50% of the day, 50%. And it's not 50% because we include weekend and night. It's 50% between 8 a.m. and 6 p.m. on weekdays. And it's actually quite difficult to measure that. And the reality is that people are not even aware of how bad the situation is because they just don't have an easy way to quantify that. But that kind of number has been reported by NYU, and we found the same thing. And that represents an opportunity waste of up to $10 billion just in the US, and also obviously delayed patient care. And so a lot of AI work has been focusing on image interpretation, biomarkers, diagnosis, disease evolution. And again, the community needs to continue to work on that. But in parallel, we believe that an upstream high-value application of AI is radiology operations, which is really not using AI to try to interpret the images and make a diagnosis, but to increase the efficiency of taking the images in the first place, really on the operation and workflow side of it. So that hospital make better use of their expensive machines, helping them increasing revenues and at the same time increasing access to MRI for the population. And you all know that AI needs data. And actually, one of the huge problems is that radiology critically lacks operational data. But there is a scheduling system from which the technologists get a patient work list and set up the scans. The scanners and text images, sometimes some images need to be repeated, and then the images are sent to the server, the PACS for radiologists. But it is very difficult today to know what really happened during the acquisition. There is just no trace of it. And that is a true operational black hole. Like, what were the protocols truly acquired? At what time each image was acquired? Was there any repeat? It's just very difficult to quantify. And as Peter Drucker says, if you can't measure it, you just can't improve it. And yet, actually, the data exists. It exists in the image themselves. Because a medical image, which is a DICOM image, contains the image data, like all the pixels, but also a trove of image metadata, including imaging parameters, timing, operator information, and many other things. And there is supposedly a standard, DICOM, but that standard is so open, so generic that vendors have done crazy things with it. And today the result is a super high heterogeneity of DICOM data with proprietary data models. And anyway, everything is siloed in servers. So there is no easy way to ask questions of it. And what we built is a platform that analyzes all the images created by MRI scanners and clean and harmonize metadata to create a new unified source of knowledge about imaging operations. And actually, it's not just about cleaning and harmonizing. When you look at it, DICOM lacks some key fundamental information to describe MRI operations. And so what we built is really a new ontology that starts from DICOM and build upon it to create a new description of imaging exams. And it took us 3 years to get it right and almost 4 million images. And now that we have that unified data layer, we kind of are like kids in a candy store. There are so many things to do, and I think we are just scratching the surface today. Just to give you an example, lots of people are interested in identifying repeat images in an exam because an image can be repeated, for example, because the patient moved and the image is blurry, making it non-diagnostic. And obviously, you want, if you are repeating a lot of things, it can quickly derail your schedule. So you want to minimize that. And we are training machine learning models to identify repeated images in an exam, and not based on some naming convention, because it just never works, it always changes, but based on patterns on the underlying imaging parameters. And from that, you can quantify the overall repeat rate. You can slice it per scanner, per date, per exam type. You can also mine from your data what is the most associated with repeats. Is it a patient age range? Is it a particular sequence? So you can really ask a question. And so here you see to really how the kind of thing to detect repeats. We are also labeling the image type with machine learning, and again, based on analyzing the image parameters. For example, here, labeling localizers, because you may be interested in quantifying repeat rate for all images except localizers, because they are just short scans, just used to quickly localize the organs before doing a longer picture of them. And again, the idea is to do that irrespective of how they are called, just because it just never works. And actually, it's funny here to see how our model correctly but labels the image 11 and 12, which are just named axial 2D plane used as a quick localizer. You just can't expect to build a filter based on acquisition name to identify that. But a machine learning on parameters easily gets it. It just has the same properties as the other things. That was machine learning on metadata. We are also doing machine learning on the images themselves. And not for diagnosis purpose, but really to quantify operations. For example, here to quantify the image quality and especially the presence of motion, so that you can then mine what is the most associated with motion. Or also by analyzing and detecting imaging protocols. For example, here with TSNE methods and detecting deviation in imaging protocols. And really the longer term goal is to use AI to go toward prediction models, smart recommendations, to automatically identify bottlenecks and propose literally optimization strategies and help radiology optimize operation and help them make better use of their expensive equipment. And it's just unreal how difficult it is today to know how well Scanner performs. And we have developed that unified data layer to get this information. And we spend a lot of time to get it right. And now I think really starts the exciting part, which is how to use this data layer and build upon it to develop upstream high-value applications of AI for radiology operation. And we strongly believe that access to operational data and AI will literally transform imaging operation. You know, we often do a parallel with the airline industry. Airline companies used to have no idea what happened in their plane and no easy access to data to optimally manage these expensive machines. And the same way airline companies today optimize operations by analyzing data from data engines, we want to help radiology to optimize operations by analyzing data from their own MRI scanners. So thank you very much for your attention.
Wow, thank you so much. If you can stop sharing your screen, I know this virtual audience wants to give you a huge virtual round of applause. That was awesome, and we really appreciate you sharing your insights with us today. For the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our amazing exhibits. Thanks so much, and we'll see you around.